presentation mode. All right. All right, so we're in chapter 1, folks. Okay? So this is chapter 1, patterns of motion and equilibrium, right? So typically in the first physics class or physical science or physics or physical science class, the first thing you deal with is motion, right? And motion, right? And motion is, when I say motion, I'm referring to the way we move through the world, right? How we get from point A to point B, okay? Right? In order for us to get from point A to point B, right, it requires us to cover a space, okay? And in order for us to cover that space, we need some time to do it, right? So, a lot of that goes back to things you learned about when you were very young, maybe in middle school, maybe some in high school. Maybe somebody took the time to talk about these things. Not me though, right? I'm not gonna spend a lot of time on Aristotle and Galileo because that's not important for us. Okay. What's important for us is to understand the mathematics that was created or that they described. Okay. But here's an outline of how the chapter proceeds, right? So we'll just move quickly through those two things and we'll get right to mass, okay? So, like I said, Aristotle classified motion in two kinds, blah, 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 okay? Then Galileo came behind him and he did something else in inertia. That's not important, okay? All those things are not important, right? Except until we get here. Okay? So that says the tendency of a moving body to keep moving is natural, right? Every material object resists change in its state of motion. This property of things to resist change is called inertia, right? So inertia is the force, right, that keeps you moving in a car accident if you don't have your seatbelt on, right? And you run into another car or object, you run into it, right? And you don't have a seatbelt on. Inertia is what's going to keep your body moving straight through the windshield, right? That's called inertia. That's the tendency of an object to keep moving, right, or resist change in its state of motion, right? So the car was originally moving, then it hit something all of a sudden, right? And inertia is going to keep you going through the windshield because you were moving with the car, okay? Now, inertia works both ways, right? Also, when something is sitting still, right? And we know that it's harder to move something that's at a state of rest than it is to move something that's already in motion. Am I right? It's harder to move something that's in a state of rest than it is already in motion, right? And we know that from our from living in this world, right? That's not hard for us to understand. That's not a concept that should be hard for us to understand, okay? And that has nothing to do with math, okay? It has nothing to do with math. We didn't talk about any equations, no calculations, nothing, right? And we're going to come back and deal with those questions later on, okay? I'm just going to move through them right now. So, mass is a measure of inertia, right? So your mass, right? Your mass is a measure of inertia. So, depending on how big you are, it's going to determine how hard it is to stop your motion or start your motion, depending on the size of the object, right? That's the mass, okay? So mass is a measure of inertia, right? Quantity of a matter in an object, right? How much stuff is there? That's what your mass is, right? Just like I told you, when you leave off of this earth, right? Which one changes? Your weight or your mass? That's the question. For anybody. No. I say when you leave, let's think about it again. When you leave off of this earth, what do we know about things that leave off of the earth? Like astronauts. When they get in space, they become what? Weightless. So what changes when you leave off of the earth? Your weight. Your mass is the amount of stuff or matter that makes you who you are. So the only way for me to change your mass is if I come and chop your arm off. Right? But your weight changes based on how far you are from the earth. And that's why the astronaut is weightless in space. So there it is, right? Weight is amount of gravitational pull. So your weight depends on gravity, right? Your weight depends on the gravity. Okay? Your mass does not depend on gravity. But your weight depends on gravity, right? And there's some equations that we'll eventually talk about, and you should be able to see that directly, right? But your weight is the amount of gravitational pull, okay? So, mass versus volume. Mass involves how much matter an object takes. Volume involves how much space. So what's the difference? What's the difference between mass and volume? Can anybody give me a good example of things that take up the same space, but they have different mass? But they take up the same space. So imagine if I had a block of styrofoam and I had a block of iron. Which one is gonna weigh more? The iron. But they both take up the same amount of space. Okay? So volume and mass are different. Very much different, right? And so those two quantities define what's called density. So that's what I just described to you, the difference, right, between styrofoam and iron. One is more dense than the other, right? That's why styrofoam is used in your packages, right? Because it's what? Somebody? Because it's what? Less dense, or it's light. So we can send it through the mail at a cheaper cost. But we wouldn't put a piece of iron to fill space in our package, would we? Right? Yes.
Can you explain the difference between mass and weight? Again, I got a little confused because you said the iron and the styrofoam would have the same volume,
but different mass.
The weight?
Yes. Weight is a gravitational pull, right? So, now that's a different analogy. Don't confound those two, or those three actually. You see what I'm saying? Like the first one I told you about was,
Astronaut.
what were we talking about the first?
The astronaut with the
Yes, mass and gravity, mass and weight, right? So mass and weight, right? Weight is a gravitational pull, right? So further I am from the Earth's surface, right? Because when I'm on Earth's surface, I weigh 180 pounds. So right now I weigh 180 pounds. But if I go on top of Mount Rushmore or the skyscraper in New York City or something, right? Or maybe even when I get up in the plane, like I just came off of, right? Your weight can change. Slightly, you might not realize it because you're not far enough from the Earth. But like I say, if you're an astronaut, you go very far from the Earth, and so you recognize the change in your weight, right? And they got like certain, I think at amusement parks, they have like, what do they call it, the gyroscope or something like that spins around, right? So in the gyroscope, it spins around really fast, and so what is it doing? It's throwing you out, right? And it's making you feel weightless because of the centripetal force. But again, so we're gonna see, that's what I'm saying, right? So don't confound those three. Just take them as one, right? With mass and weight, think about that as the astronaut. When he leaves the Earth, he gets weightless. So that means what? That means mass and weight are not the same. Right? Period. Stop it right there. Now, when we talk about mass and volume, right? Because with the person, you're not changing their volume. So that wouldn't be a good analogy for that one. You see what I'm saying? That's why I say don't confound all three of those, because one is not good for all of them. That's why I separate them like that. But in the case of the iron again, like I said, you got two blocks, same size, same dimensions, length, width, and height. One is just styrofoam, one is iron. Obviously, the iron weighs a lot more because it's more massive. Because the gravity pulls on it, right? It pulls on it at at the same rate, but it weighs more. It has a different weight, right? Okay? Any other questions? Anybody else got any clarification that they want me to make? But like I said, we'll go through this, and we'll go through the little questions, and maybe that'll clear some things up for you. All right? So again, right, your mass, right, we measure mass in grams or kilograms, okay? In kilograms. And so kilograms, right, can be converted to newtons, right, which is a force, okay? So your weight is a force due to your mass. Y'all following me? Your weight is a force, all right? That's why if you weigh more, right, you're gonna do more damage when you hit somebody, right? So your weight is a force, which is a consequence of your mass, of gravity pulling on your mass. Okay. And so again, we talked about the difference between mass and volume, and we talked about the styrofoam and the iron, right? The difference between those two is density, right? Mass divided by volume, right? We're all familiar with these terms, right? Mass divided by volume. So that's how we calculate density. And I think in one of your labs, you'll actually do this exercise. All right? So, a force, right? So for something to move, we need a force. All right? Things just don't move by themselves. Okay? Things don't move by themselves. All right? We need a force for something to move. If something's moved, then that means a force has acted upon it. You might not see the force, right? If you walking underneath a tree and the apple fall out the tree and hit you in the head, right? Like it did to Newton, right? Then you know that there was a force that acted upon the apple because it moved. It changed its state of motion. It was at rest and it started moving. So there had to be a force that acted upon it. Okay? And so a force is a what? Push or a pull. That's simple. Right? Like in a tug of war. So push or a pull. That's what a force is. Okay? And oftentimes we have more than one force which acts on the same object. Like I said, a tug of war. Right? In a tug of war, we have folks pulling on one side, the other folks pulling on the other side, right? And then we have the little flag in the middle, right? So if the folks on this side are pulling with 10 newtons, right? And well, according to this plot, right? Let's forget about that for right now. I'll go back to that because that's not gonna make sense here, right? But if I put two forces of 5 newtons on this object in the same direction, right? Then obviously they do what? Add together, right? Because they're in the same direction. So those forces are gonna work with each other. All right? Here, right? This is what we're talking about, right? Well, this is a 5 going in this direction, 5. That's like the tug of war where they're equal forces on each side. So the flag doesn't move at all, right? But soon as I exceed the amount of force on one side or the other, that's which way the object moves, okay? So that's a net force. That's what we call a net force. When there are more than one force acting upon an object, right? We have to calculate a net force. That's like a net paycheck, right? Or whatever they say, net pay, right? When you have more than 1 or 2 taxes you got to pay on your paycheck, you get a net pay. All right? Yeah. All right. So we have something called the equilibrium rule, right? And the equilibrium rule just says that the forces are equal. All forces are equal. That's what the equilibrium rule means. It's that when I sum up all the forces, sigma stands for sum, right? This is a sigma, Greek sign for a sigma, right? It means we add all of the forces together, and we should get a 0, right? If the object is at equilibrium, right? So this object is at equilibrium right now. This is at equilibrium, right? You're sitting at equilibrium right now, right? So that means every force that's acting upon you has been equilibrated, right? It has been equaled out. All of the forces that act upon your body right now have been equaled out. That's why you sit still. You're at equilibrium. Oh, I'm right here. All right, so, and we'll talk about that. So, an object that moves at a constant velocity is said also to be in equilibrium, right? So the question is, can an object in motion have 0 acceleration? I'm asking y'all. I'm asking one of y'all. Where's that roll at? Who got the roll? Everybody sign? I'm asking y'all, can an object be in motion without accelerating? No. Huh? Can an object be in motion without accelerating? Hmm? Yes?
Without accelerating.
Like,
What does it mean to accelerate? What does that
can
mean?
it get in motion or can it like be in a state of motion?
Can it be in a state of motion without accelerating?
I'm gonna say yes.
Okay. Everybody following that?
Yeah, I'm with you.
You with me?
Yeah, I'm with you.
You sure? Positive? Alright. So let's see. Well, we'll see. We'll see. Alright, we'll see. I'm not gonna waste time on that. But so when two or more forces cancel to zero on a moving object, then the object is in equilibrium, right? So yes. So the answer to the question is yes. The answer to the question is yes, an object can be moving but not accelerating. What is the definition of acceleration? What does that mean to accelerate?
Speed up.
To speed up, to change speed. So can you be moving without changing speed? Yes. Very much so. Right? So it doesn't necessarily mean that you got to be sitting still to be at equilibrium. That's the point, right? An object can be moving, but be at equilibrium, right? An object can be moving, but be at equilibrium, right? Yeah, so an object can be moving and be at equilibrium, right? And one of the, one example of that is the Earth, right? It's the Earth. Right? We don't feel, we sit here and we do our thing and we move about the earth like it's sitting still. Is the earth sitting still? No. It's moving very fast. All right? But you don't, to you, doesn't seem like it's moving at all. All right? But the earth is moving very fast. Okay? It's kind of like sitting on an airplane, right? You get on the airplane, right? You might, especially when it gets up to the cruising altitude, you might feel like you anywhere, But that airplane, trust me, is moving very fast. Very fast. Faster than you can comprehend. Because you drive around in cars. Stuff like that. So you can't wrap your head around how fast an airplane is moving. Okay? And definitely not light. So that's a whole nother story. Alright? But now let's talk about friction. Okay? We all know what friction is, right? When we rub two things together, especially two metals or something like that. We rub two surfaces together. Those surfaces generate heat, right? Because on a microscopic scale, those surfaces are rough. They are not smooth. They just look smooth to you. Okay? They look smooth to you, but on a microscopic scale, those surfaces are rough. Okay? And so when we rub two surfaces together, two materials, right? We generate heat. Okay? And the amount of heat, right, it generally depends on, right, the type of materials, how long we rub them together, what we put in between them, like oil for your gas, for your car, right? You don't change your oil in your car. That oil degrades over time, becomes sludgy, right? Doesn't give you the proper viscosity, so your car can run properly, and your engine locks up eventually. Okay, that's just a fact of nature. Okay, that's friction. And like I say, that's not anything which requires a lot of thought, because we know what friction is. We live with friction. We encounter friction on a daily basis. So don't think of it as something foreign to you. Okay? So again, speed is, like I said, we're talking about motion, right? Speed is the distance covered, right, per amount of travel time. That's what speed is. So in order for me to define the speed of anything, I must define what distance the object covered and what time it took the object to cover that distance. Okay? That's speed. Okay? Now they got two types of speed, right? Average speed, right? And instantaneous speed. Okay? So, what's the difference? Average speed is exactly what it is. It's an average, right? It's an average. It means if I drive, if I'm going to New Orleans and I start off at 100 miles an hour, then I drop down to 50 miles an hour, right? And I end up in New Orleans, then my average speed is going to be what? 150 divided by 2, right? I took 100 and 50, added them up, divided by 2. That's average speed, right? But what if I asked you, well, on that same trip, what if I say, well, how fast were you going when you got on the Pontchartrain bridge? How fast were you going in? You couldn't really tell me, right? Because all you could say is what? I'll give you an average, right? But I can't tell you how fast I was going at that time. That's the difference between average speed and instantaneous speed. Okay? Instantaneous speed tells you how fast at any time. Okay? It's a little bit more accurate than an average. Okay? But we're going to deal mostly with average in this class. Instantaneous is like a higher level of mathematics. Okay? So, again, motion is relative, right? Everything is always moving, right? Everything is always moving, right? So, in the universe, we're said to, if something has no motion at all in the universe, right? That doesn't exist. That's a concept that does not exist in our world. Okay? Where something can exist and have no energy. That doesn't exist. Okay? Anything that has mass has energy. Okay? That's from Einstein. Okay? But if it has mass, then it's made up of atoms and all of these things, right? And even atoms are moving, right? They don't move very far, but they are moving and they have energy. Okay? So it says at this moment your speed relative to the sun is about 100,000 kilometers per hour. So we don't think about things in, kilometers per hour. I think on your dashboard in your car is what, miles per hour and kilometers per hour. But definitely your dash doesn't go up to 100,000. Okay? But you can think about how fast this is. 100,000 kilometers per hour. Okay? Your car might go, what, 200 best? Okay? All right, so acceleration. So that's what I said. That's why I asked you earlier. Well, what does it mean for a thing to accelerate? For something to accelerate, it means that its speed changes. It either speeds up or speeds down or slows down, right? And in the case where it slows down, then we call that deceleration. Okay? And so we have an equation for acceleration right here, right? Like I said, what is acceleration? Acceleration is a what? Change of velocity. Change of velocity. So in order for something to accelerate, it has to change velocity. And it does it in a certain time interval. Okay? And so one example of acceleration is free fall, right? Free fall is an example of acceleration. So, when an object only experiences gravity, that's the only force that the object is experiencing is gravity, right? That's called free fall. All right, so if we were to plot this, we could actually plot this and we would get a particular type of curve. We're not going to do that here, but yeah, I think this is it. All right, so but what this says is that what? Time of fall, right? So here we have seconds, right? And here we have velocity, right? So if I have an object, or like this, right? So time 0 is right here. And distance 0 is right here, right? When I let it go, right, exactly 1 second later, if I caught this exactly 1 second later, it would be traveling, say it, 10 what? 10 what? Not milliseconds. That's not milliseconds. Meters per second. Milliseconds is a unit of time. I asked you how fast, right? Velocity, right? That's what it's saying. It's saying that after 1 second, the object is now traveling 10 meters per second, right? And it's covered a distance of 5 meters. After 2 seconds, my object is doing what? 20 meters. So what has happened? Huh? Say it again. I can't hear y'all. It accelerated. Right? It went from 10. It accelerated right here too, right? It went from 0 to 10. That's acceleration. From 10 to 20. That's acceleration. So as it falls towards the earth, it's doing what? Getting faster and faster. Right? And same is true, right? There's a certain rate. Right? You see how this number stays the same. Right? After every second, I gain 10 meters per second. And you all going to see that. Right? It's an equation for this. But after every second, if I just drop something, after every second, the earth makes that object speed up 10 meters per second every second. Okay? And like I said, we can plot these things, right? This is an actual, so in a lab, we would take data, right? And we would take this data and we would put it in a spreadsheet and we would plot it and it would give us a certain graph, okay? But, and you'll get a chance to see that. But the point here is to demonstrate to you that when something is in free fall, right? Because that's what we were talking about, right? We were talking about free fall. Free fall, right? After every second, 2, 3, 4, 5. After every second, I gain 10 meters per second. Okay? All right, so hopefully you are on Mastering Physics because I'm going to upload some stuff for you to do. Yes, ma'am. Well, you're not signing up correctly. Okay, so I pointed to you all of the people who have signed up correctly. I would suggest you go ask them what they did because I am not a student, so I don't see your side. So I suggest you go and find one of the students who signed up correctly. So let's call them out again. All right? Carson Bennett, Christian Garcia, AJ Jeffries, Kamari Johnson, Tori, I think Tori left, Cameron McMorris, Antonio Sanders, and Mike. I would suggest you go and ask one of them, okay? I would suggest you do that. They could probably help you better than I can because I'm not a student. I don't see the same thing you see, all right? But I see who has signed up correctly, though. I see that. All right? Any more questions? Concerns? Refresh what? Huh? Oh, all right. Well, yeah, I got some more people. Yo, Byron Wyatt. All right. Sanaya Williams. Sanaya Williams. Huh? Oh, yeah, son.
It's an option on there.
What you say?
Option, HOV, that's on. Yeah, right here. I was stretching like the beat. Six and stuff like my stuff is down here.
It just shows you what.
It shows
Huh? Oh, I'm sorry.
Thank you.
I don't know. I'm trying to where's the person?
Like I say, man, you do better asking somebody else, one of your classmates.
They telling me to click it, but it
Nah, theirs really looking different. Cause you
Oh,
know
yeah?
how you said
you had to leave.
when you tap on the link, it said the temporary access. That's how mine was. Theirs is a whole different stuff. Mine wasn't like that. So it really might be on
Yeah,
either
might not.
Pearson.
Yeah, all
Like
right.
it might be a problem with that. I don't know. Mine didn't do that.
Let's see. Well, all right.
Is there a way like you could get a refresh link?
This is the refresh link.
like it's still saying my old registration that kind of like it's not deleted.
Oh no, I deleted that. I deleted that. Can't say that. I deleted that.
Oh, because it's saying it expired.
What expired?
The dates enrolled
Oh, let's do
for the
this.
thing.
Alright,
That's
let's
probably
do
why
this.
it's saying that.
I could probably change that.
So you got in there? You paid?
No, you don't have to pay for anything. The university.
paid.
Yeah, don't pay for nothing. Let's see. Let's do this. All right, give it. We got to give it a second to update. But I changed it. I changed the enrollment date. Yeah. But it said give it. It said editing course details. So check back later. All right. So just keep checking it, and I'll extend it a couple days. The assignment. But keep checking it. And the introduction assignment. What introduction?
I was gonna ask you, is the lab in conjunction with this class?
Oh, no, I'm not. No,
I know
you should.
you're
You
not
should.
over the lab.
Yeah, I'm not over the lab. That's not me.
But is it supposed to be like?
Yeah.
overlap?
They are related. Yes, but I don't do the lab though. That's a different faculty member.
Because I was about to say we did take a quiz,
Okay.
but we didn't learn none of this stuff.
Yeah, so you got to talk to whoever the instructor is for that lab. That's not mine. I didn't.
Is our book connected though to that class? Like what we're reading for this class? Is that?
That's a lab class. So your book is for lecture, but what you do in lab relates to what you do in lecture, but it's not the same book.
So the book that we read for this class is not gonna have the
Oh, they are. You're not gonna use that book, but they are related though. You understand what I'm saying? It's not. You're not gonna take that book to lab class and use it. But the stuff inside of that book is what you should be doing in lab.
Because right now we're doing
You following me? Because you look like you.
like they connected, but they not.
Yeah, Marshall. Yeah, that's probably who your lab teacher is. Okay, but the laboratory class, the book that, like I said, I don't know if there's a book for the laboratory class because it's not my class. Right? Huh? I wasn't here Friday. I wasn't here Friday.
No, that's a different class.
I wasn't here Friday.
Not for this one, for registering, right?
Okay.
Like,
You trying to register?
That's what I'm saying. Like, it's not a.
Well, I reported.
No, a
I
lab-
think I
a lab
reported.
is like,
I think
you
there
know
were
how
like
this-
5 people
what's this physical
who I couldn't
science-
find on any of my
Like,
lists.
this
Yeah.
is
Oh, yeah,
this
look.
class worth
So-
3 credits, and in physical science
Hopefully
lab,
it wasn't
that's
you.
a whole different course.
Look, I think I signed up for it. Well, I think I just signed up for it right here. I'm gonna take this right here. Then it sent me an email. But let me see.
Uh-oh.
So I went to this right here.
Mm-hmm.
Yeah, I think I'm. Let me go back. Let's see. Yeah, it keeps.
So it's still not working?
That's how it looked though. Go back.
That's how it looked when you did it?
Because
That's-
it just was
right
working,
here.
but I don't know.
It started like this.
Mm-hmm.
Like that's how mine went. Then I tapped that, and then it worked. That's how you call my name. That's how mine went.
Yeah.
But his saying an error.
Because it just was working though. Cause look, I just got.
It's
the
probably because you
email.
got it open on different.
Oh. And give it some time,
Because I
because
had
it
did
still say
earlier,
right
that's
here,
what they sent me
editing.
earlier.
You got to give it time, brother. You got to give it time to update. So I would go.
Oh, then you good.
I'm good.
Yeah. It
What's
says-
your name?
It said he registered.
What is your name, man?
Quentin Butler. Right there.
Yeah, Quentin
Oh,
Butler.
then you good. You in there.
I'll just have to make sure. 'Cause I'm
Yeah.
sure I'm
Once you close all of that, you should be good. Because you probably just got it open on too many browsers and all that.
it's good.
But
So far I'm saying for like assignments.
but you got your username in there and all that. You should be able to do
Mhm.
it.
I'm saying like assignments though. Like we good.
Nah,
Just
yeah.
go to
We haven't
mileage.
gotten none yet.
Okay.
That was just. This was the assignment.
Okay.
Registering.
All right. I got to make
That's
sure.
what he trying to get everybody in first, but he gonna start uploading stuff.
All right, brother. Thank you.
You got it, man?
Yeah.
All right.